Okay, guys, so we've talked about blood. Now we're going to talk about the heart. You know, that little thing in the middle of your chest that keeps your blood flowing and circulating, working 24 out of the rest of your body, even when you're sleeping. Your heart's located in the thoracic cavity in the mediastinum. Remember way back the first week, the thoracic cavity actually has two pleural cavities and the mediastinal cavity, and that's where your heart is. It kind of tilts towards the left, and 2/3 of it extends to the left of the body's midline, but it's still kind of underneath the sternum right there. Remember, the sternum is what we are pressing on when we're doing CPR. The broadest part of the heart, or the base, and this is kind of weird because it seems backwards, the base of the heart is actually towards the top, towards the upper right, and the pointed end, or the apex, is at the lower left. So apex and base don't always mean the upper and the lower. In this case, the base of the heart it's the widest part, and that's at the upper part. The point of maximum impulse, where the strongest beat can be felt, or where you can hear the heartbeat the best, is located at the apex, and that's between the 5th and 6th ribs, I think, mid and almost mid-clavicular. The great vessels, the vena cava superior, the vena cava, and the aorta enter and leave the heart at the base. So the vena cavas come into the heart at the base, and the aorta leaves at the base, at the top, not at the bottom. So the heart structures, there's a double-walled sac called the pericardium that surrounds the heart, and it's anchored to the surrounding structures by ligaments and tissues. And of course, there's more layers. The pericardium has two layers, the outer one being the fibrous pericardium. That's kind of a loose-fitting sac of its really strong connective tissue. And then the serous pericardium covers the heart surface itself. Now there is a potential space in there, so that as the heart beats, they can slide across each other and not rub against each other, because that would be pretty painful. The serous pericardium also has two layers. At the heart's base, so at the top of the heart, it folds back on itself to form the parietal layer, which lines the inside of the fibrous pericardium, and the visceral layer, which actually covers the heart surface. The pericardial cavity exists between these two layers and contains a small amount of serous fluid that helps prevent friction as the heart beats. The heart wall itself has three layers. So here's the parietal layer of the pericardium. Here's that pericardial cavity with the fluid, and then we have the heart wall itself, this whole part here. There's three layers to that. The endocardium is the very inside. That lines the chambers, covers the valves, and it continues into the vessels. It's a very thin layer of squamous epithelial cells. The myocardium is the actual heart muscle itself. That's the cardiac muscle cells. It's the thickest of the three layers, and it's really the one that's doing the work of the heart. That's what's contracting and pushing the blood out. The epicardium is another thin layer of squamous epithelial cells that covers the heart surface. The epicardium is the visceral layer of the serous pericardium. So I know that's a lot of different pericardiums, but I want you to understand the different layers and why they're in those different layers. The heart contains four hollow chambers. The two upper chambers are the atria, and the two lower chambers are the ventricles. The atria serve as reservoirs. They receive the blood from the body or from the lungs, and they're separated by the interatrial septum. So here's the atrium right here. Here's one of them. This is the right one. The left one is a little harder to see. It's kind of tucked behind a few things. And then the interatrial septum is right here in between the two of them. The walls of the atria, they're not as thick as the walls of the ventricle because they're really only moving blood a short distance from them into the ventricles. The ventricles receive blood from the atria and pump it either to the lungs or to the rest of the body. And the two ventricles are separated by the interventricular septum. So here's the right ventricle right here, this whole thing. And here's the left one. Right here is the interventricular septum. That's what's pushing them apart. The ventricles pump blood a little further than the atria do, so they generate more force. The walls are thicker. The left ventricle, because it has to push blood throughout the body, its walls are thicker than those of the right ventricle because the right ventricle pushes blood out to the lungs. The great vessels, the superior and inferior vena cava, right here's one, and here's one. This is the inferior vena cava, this is the superior, and they're called those because one's above, one's below. And remember, this is the base of the heart, the widest part. That's where the blood returns to the heart from the body. And then the pulmonary arteries are right here. That's where the blood is going from the heart to the lungs. The pulmonary veins right here are the ones that are returning the blood from the lungs to the heart. And then the aorta, the largest blood vessel in the body right here, this is this right here, that carries the blood out to the rest of the body. When we do the vascular system, you're going to learn there's a lot of branches off of the aorta that get blood out to every part of your body. There are strands of fibrous connective tissue called chordae tendineae that go from the floor of the ventricle to the valves. That's what these are right here, these little things here. These are the papillary muscles. These little things right here that keep the chordae tendineae in place. The papillary muscles contract with the ventricles, which pulls on the chordae tendineae, anchors the valve cusps in the right position. The heart valves, we kind of cut a cross section and we're looking at it from above now instead of in front or in back. Each of the heart's 4 valves are formed by either 2 or 3 flaps of tissue called cusps or leaflets. There's 2 atrioventricular valves. Those are the valves between the atria and the ventricles. And then there's 2 semilunar valves that regulate flow between the ventricles and the great arteries. So the right AV valve, called the tricuspid valve because it's got 3 leaflets, that's this one right here. The leaflets are, this is the extension of them a little bit. It's hard to see on this picture. This works to prevent backflow from the right ventricle to the right atrium. So it helps to make sure the blood is always flowing from the atrium into the ventricle and not going back. The left AV valve, called the bicuspid valve because it's got 2 leaflets, also known as the mitral valve, that prevents backflow from the left ventricle to the left atrium. Semilunar valves are the pulmonary and the aortic valves. The pulmonary valve prevents backflow from the pulmonary artery to the right ventricle. So remember, arteries carry blood away. So the pulmonary artery is what's taking the blood from the heart to the lungs, and the pulmonary valve prevents blood from going back to the heart before it gets to the lung. Then the aortic valve prevents backflow from the aorta into the left ventricle. There's a semi-rigid, fibrous network of things, connective tissue called the skeleton of the heart. This skeleton encircles each valve. The skeleton is intended, it supports the heart, it keeps the valves from stretching. It also provides some insulation between the atria and the ventricles, which prevents those electrical impulses from reaching the ventricles by any way other than through the normal conduction pathway. We're going to learn about that in just a minute. Listening to heart sounds, when the heart valve closes, they produce vibrations that can be heard with a stethoscope that you put on the outside of the body. I don't know how many of you have ever had your doctor listen to your heart. But if you think of it kind of like how a door closing makes a sound, and by listening in key areas, you can identify the sounds that each valve can make. This is really something that a cardiologist is very good at. Some physicians are pretty decent at it and can recognize if there's an abnormality. It's not something we're going to expect you to do. So it's not even something I'm going to expect you to be able to tell me if you listen in this one spot, you're going to be able to hear which valve. So the path of blood through the heart, there's no connection between the right and left sides of the heart under normal circumstances. There are some birth defects that do connect, like the ventricle. There's an opening there that, like here, there's an opening that exists when you're first born. It's supposed to close up very quickly. If it doesn't, that's an abnormality. But under normal circumstances, there is no connection. The blood from the right side and the left side should not be mixing. Both the right and left atria contract at the same time, and both ventricles contract at the same time. So the right atrium gets blood back from the body through the inferior vena cava here and the superior vena cava here, and it's coming to those two from other veins coming from the body. The blood goes into the right atrium where it collects until the atria is full and it contracts. When the atria contracts, it forces the tricuspid valve open right here, and the blood pushes into the right ventricle. When the right ventricle is full, and now we're over on this side, the right ventricle is full, the tricuspid valve closes, and that's the sound you hear when you're listening to heart sounds. And that's to prevent the blood from going backwards into the atrium when the ventricle contracts. The right ventricle contracts, forces the pulmonary valve open here at the pulmonary arteries, and pushes the blood on into the lungs, out through the pulmonary arteries this way and this one over here. After it empties, then the pulmonary valve closes, and that prevents blood from going backward into the ventricles. After the blood gets to the lungs and replenishes its supply of oxygen and gets rid of the carbon dioxide that it's brought from the rest of the body, it then enters into the pulmonary veins and returns to the heart, to the left atrium. And here, now we're on this side already. So here the blood is coming back from the right and left lung through the right and left pulmonary veins into the left atrium. When the left atrium is full, it contracts. That forces the mitral valve or the bicuspid valve to open and push the blood into the left ventricle. When the left ventricle is full, this mitral valve closes, and again, that's the sound you hear when you're listening. And then the ventricle contracts, which forces the aortic valve open and pushes the blood up into the aorta to be distributed out to every organ of the body. You do have coronary arteries that serve your heart muscle itself, the right coronary artery and the left coronary artery. These are filled right at the end of the left ventricular contraction. The blood, once the blood gets into the aorta, then it can also go into these two arteries. The cardiac conduction, you remember we talked about those intercalated discs in between your cardiac muscle cells, and they are what helps to conduct the electrical signal for your heart, because your heart muscles have this little thing called automaticity. So your heart muscle can make its own heartbeat, basically. The impulses they go through a specific route through your heart. So they start in the sinoatrial node right up here. That's at the top of the right atrium, and that sends off a signal through the interatrial bundle that sends the impulses to the left atrium as well. So it goes over here. The left atrium and the right atrium contract together when that happens. Then the impulse enters the AV node. This is the atrioventricular node, called that because it's between the atria and the ventricles. The impulse gets there, it slows down a little bit because it needs to give time for the atria to contract and the ventricles to fill. The heart skeleton, again, that insulates the ventricles, making sure that these impulses only go through this node here. After it gets through the AV node, it picks up speed again and travels down the bundle of His right here, number 4. It's also called the AV bundle. And then from there, it goes into the right and left bundle branches, right here. And then out into the Purkinje fibers right here, which causes then the muscles of the ventricles to contract. And the ventricles, again, contract at the same time, same as that both atria contract at the same time. The SA node is really, that's the primary pacemaker of the heart. That's called the pacemaker of the heart. That can fire at between 60 and 80 beats per minute. If the SA node fails, then the AV node here can take over, and that can take over firing at a rate of 40 to 60 beats per minute, so it's slower. If the SA node and the AV node both fail, the Purkinje fibers themselves can initiate impulses, but only at a rate of about 20 to 40 beats per minute, and it's really not enough to sustain life for very long. I'm Sure, you've all heard about electrocardiograms. This is the thing that traces the heart, the electrical conduction of the heart on a piece of paper. When you get to cardiology, cardiovascular and circ in the med-surg section in semester 2, you're going to learn what each of these sections mean. Basically, this is really a very normal EKG. It's got the P wave is when the atria are, that signal is spreading from the SA node to the AV node and the atria contract. The QRS is when the ventricles contract. And then the T is when the ventricles are relaxing. You don't see when the atria are relaxing because it's kind of buried in this QRS, big old QRS complex here. Really what I want you to know is that the EKG represents the depolarization that happens as the cardiac muscle contracts. I'm not going to ask you to get any more detail than that, but you are going to have to remember all of this for when you get to circ and med-surg. A cardiac cycle is a series of events from the beginning of one heartbeat to the beginning of the next. So one entire heartbeat is a cardiac cycle. It consists of the contraction, which is also known as systole, and the relaxation of the heart, which is known as diastole. And I remember this because if you take the D from diastole and the R from relaxation, it makes DR, which is doctor. I can't think of any other way to think of that. There are phases to the cardiac cycle. I'm not going to expect you to know that. I do want you to know how the blood flows through the heart and how the electrical system is conducted through the heart. Cardiac output really refers to the amount of blood your heart pumps in 1 minute. And a way to determine cardiac output is to take the heart rate and multiply that by the stroke volume. The stroke volume is the amount of blood that is pumped with each heartbeat. An average resting cardiac output is between 5 and 6 liters a minute. If you think about that, that's an awful lot of fluid for your heart to be pumping. Stroke volume is something that is calculated after doing a test like an echocardiogram, something that can look at how well your heart is pumping. It's not something you're going to just know. The doctor's going to have to decide that. The heart rate, obviously, you can figure out, and then you just multiply the two. So what things can affect a heart rate? Part of it is age. A newborn will have a heart rate at about 120 beats per minute. Young adult women have heart rates of 72 to 80, and young adult men have heart rates of 64 to 72. You do need to know a persistent slow heart rate, something that's less than 60, is called bradycardia, and you should have learned already that brady refers to slow. And then tachy then refers to fast. So tachycardia is a heart rate that's over 100. The heart generates and maintains its own beat, but the nervous system can alter the heart's rhythm and the force of contractions. So for example, if you're exercising, if you're out running, if you're swimming, if you're doing even just yard work, or for some people even just running the vacuum is quite a lot of exercise. That stimulates the acceleratory center that's in the medulla of your brain, and which then sends out some impulses through the sympathetic nervous system. And remember, the sympathetic nervous system works to increase your heart rate. So the sympathetic nervous system says to the heart, hey, we're detecting some things that are saying you need to beat a little faster, get a little more blood out there. Something like a high blood pressure will stimulate the inhibitory center in the medulla. The inhibitory center sends signals via the parasympathetic nervous system. Remember, that's the one that slows things down, to kind of try to bring your blood pressure back down. Input, oh my goodness, to your cardiac center in the medulla, it gets input from multiple sources. Proprioceptors signal changes in physical activity. Those are the ones that say, hey, we need a little more oxygen. Can you pump a little faster to get some more blood to us? Those are out in your muscles and your joints. Remember, proprioception is that awareness of where your body is and what it's doing, where your hands and your feet are at all times. Baroreceptors, also known as pressoreceptors, those are in the aorta and the internal carotids. Those sense the change in blood pressure. If the blood pressure falls, it's going to send a signal to make your heart beat faster to increase the cardiac output. And then chemoreceptors in the aortic arch, in the carotids, and the medulla can detect changes in carbon dioxide, decreases in oxygen, and decreases in pH. In response, the sympathetic nervous system is going to tell your heart to beat a little faster so that stroke volume goes up and circulates more oxygen. There are things that can affect your stroke volume, and remember, stroke volume is the amount of blood your heart pumps in one beat. Preload, contractility, and afterload. Preload is the amount of tension in the ventricular muscle before it contracts. So obviously, if there's more blood, your heart needs to stretch more. If you think about like a rubber band, you pull back, the further you pull back on it, ideally, the further it's going to go when you shoot it. So the amount or the tension you place on it is called the preload. Contractility is the force that your heart pumps with. The more the ventricle is stretched, the more forcefully it will contract. And again, you can also think of the rubber band. If you only pull back a little bit and let go, it's barely gonna bounce at all. You pull back further, it's going to go further because there's a more forceful contraction with it. This is called Starling's law of the heart. Afterload refers to the forces that your heart must work against. So an increase in afterload, like in high blood pressure, pushes against the blood coming from your heart, which leads to decreased stroke volume. So like if you try to fire that rubber band off underwater, the pressure of the water is going to resist the forward movement of the rubber band. Two things we're going to talk about are left ventricular failure and then right ventricular failure. Left ventricular failure means that your left ventricle is not pumping as well as it should. It doesn't mean it's not pumping at all. It just means it's not pumping everything it should be. So not all the blood is leaving it, and then that means that there's not enough room in it for the blood to come from the atrium into it. And remember, your left ventricle pumps blood out into the rest of your body. So if it falls behind and not all the blood is going out into the body, then there's not as much room for the blood to come back from the lungs. So the blood's going to wind up staying in the lungs. You're going to get a buildup of fluid there. And then you're going to get short of breath. The buildup of fluid is called pulmonary edema. Coughing, if it continues on, that's something else that could wind up being fatal. And last but not least, right ventricular failure. If the right side of your heart does not pump well enough, so it's not pumping all of the blood out to the lungs, then the blood, there's not enough room for the blood to come back from the rest of the body. So it has the effect of blood backing up, fluid backing up into the rest of your body. That's when you see swelling, like swelling of the feet. You can also see like enlargement of the liver, pooling of fluid in the abdomen, that's known as ascites, and distension of the jugular veins, those veins in your neck. That we're going to learn about those next week. And failure of one ventricle places an added strain on the other ventricle. Eventually both of them are going to fail. This is something that if it's not dealt with and managed, it could wind up being fatal. So we've talked about this week, the first podcast was about blood and its components, and then this one is about the heart, the different parts of the heart, the valves, the blood flow through the heart to the lungs and back to the heart, the electrical conduction of the heart, some things that can affect the heart rate, and then some problems with failure of the heart to pump as well as it could. As you can tell, it's a pretty important organ. You kind of need that just like you need all the rest of them.